I am co-advised between Professor Pranay Narang here at Harvard-Seas and Professor Polina Anakeva at MIT, and we're looking at carrier transport across nanoscale interfaces. Specifically, we're interested in looking at phonons, so heat transfer across these really nanoscale interfaces, because we know that the conventional macroscale laws like Fourier's heat equation sort of breaks down at those length scales and time scales. So we know that when we bring two bodies in contact and they have different temperatures, heat must flow from the hot side to the cold side, like imagine holding like a bar of metal and heating it on one side. However, as we decrease the size of that material, some of the fundamental laws and what we would expect kind of break down. So we're trying to figure out what happens at those length scales and time scales, and specifically what happens when two dissimilar materials are brought in contact together at that interface. Well, it's important to me from a fundamental perspective. I think we want to understand why it works and why we can't really capture the physics behind it. But from an applications perspective, it could find use in thermoelectrics and device implementation. So for example, in microchips, a lot of the connections that are made could be interface limited, and they could be dissipating a lot of heat at those interfaces. So understanding the structure of the interface and the interface dynamics of those carriers can then help us design better interfaces that would minimize those heat losses at microchips, for example.